All right, welcome to video number 4. Here, what happens if we don't want a left Riemann sum rectangle? What do we want to find a right Riemann sum rectangle? And at the beginning, you might say, well, why does it matter? And you're going to find out here why it does matter, number one. But also, number two, when you're working through the AP exam, it's going to specifically ask you to find one of the approximations, whether it's a left-sided approximation, a right-sided, or a midpoint approximation. And so we have to make sure that we know how to do each of those independently. Can we use a right Riemann sum with two equal subintervals to approximate the area between the curve VQ of t and the t-axis from 0 to 2? Again, this is something that's pretty familiar, I think. We're looking for this area under the curve, but we want to break it up into two subintervals. So the first subinterval, will be from 0 to 1, and then the next subinterval will be from 1 to 2. That makes our width, which I'm going to denote with the symbol delta t. The change in t is 1. That's our width for each of the rectangles that we're about to build. However, we're going to do right-sided Riemann rectangles. If we do right-sided, then I'm going to start on the right side of my interval. So I'm going from 0 to 2. I'm going to start on the right side, and I'm going to go all the way up until I hit the curve, and that's going to determine the height. Come back and go all the way down. There's my first height and my first rectangle. And then I'm going to start from 0 to 1, my next sub-interval. I'm going to start on the right side, which is 1, go up and hit it, and then come back and down. So what do we know here? Well, if I find the area 1 and area 2 of these two rectangles, it's actually going to be too much, right? These rectangles go over the shaded region. So what we're establishing here is an estimate, but this would be an overestimate of what we need. We're looking for the integral from 0 to 2 of VQ of t dt, and we can approximate that with the area of this first rectangle, which is VQ of 1 times delta t. And then we're going to add VQ of 2 times delta t. Why am I writing these as symbols? So that you can see there's a pattern, right? V of 1 means the y-coordinate, the height of the curve at 1, which, by the way, we already calculated was 1.5, times delta t, which we just said is 1, plus V of 2, which is this height, is the height of the curve, V, at time 2. We could do this and use the formula to get the answer. I can look at the picture and see that it's 3, but I just want to make sure that you know that the formula will also give you that this is 3 times delta t, which is 1. And so here we now see that this is 4.5. So this is way over what we need, right? So I've now established that this is an overestimate of the actual area under the curve, which is this integral that we're looking for, whereas the previous was an underestimate. And so now the actual retail price is somewhere between 2.5 and 4.5. A lot of students will guess, is it 3.5? Because that's halfway in between. Well, maybe, but we need to get maybe a little bit more information on where it is. So here's what we need you to understand. We used one rectangle, and by the way, this is a left Riemann sum rectangle, and we shaded some space, but not all of it. We drew two rectangles. These are left-sided Riemann rectangles. We shaded a little bit more. What would happen if we shaded 4 rectangles? Do you notice how this empty space keeps shrinking? At first, there was a lot of space that I didn't get. In the second example, I shaded a little bit more. In the third example, I shaded a little bit more. When I come to this one, there are 8 rectangles here. So the more rectangles we create, the better our approximation becomes in general. Right? The more rectangles we draw, whether it's left-sided, right-sided, midpoint rectangles, the better my approximation is going to be. And if we follow that thought, then if we want to find the exact area, how many rectangles would we need to draw? Well, we would need infinitely many rectangles. If the more rectangles we get, the better the approximation. If we draw an infinite number of rectangles, there are going to be so many rectangles you won't be able to see the little empty spaces there because there's so many, and it just sweeps across that area that we want. So we want to make sure that you understand what we're talking about here. When we talk about a Riemann sum, we're talking about a rectangle, right? N represents the number of rectangles. In this case, N would be 3. In the cases that we did, we maxed out at N2. To find the area of each rectangle, we're always multiplying the length times the width, or the height, which is f of x, times the base, which is delta x. Our examples use t instead of x. If I want to find the total area, well, then I'm going to use a sigma notation, because if you recall, the sigma notation represents a sum. So we're going to add all these areas to get the total area created by the Riemann approximation. What are we adding? We're adding sigma from 1 to however many rectangles there are. Well, there are n rectangles. And then what happens with each of them? Where the area is always f of x, the height, times, or the length, times delta x, which is the width. So notice this right here is just length times width. That's how we find the area of a rectangle, right? And so in a very real sense, we've walked through the idea that visually I can see a rectangle. The area of the rectangle is going to approximate the area that we want. So I need to multiply this dimension by this dimension, which means we need to set up this. Oh, but there's multiple rectangles. So that means I need to add up a bunch of these. And in this case, we get the total area. But if we want the exact area, then we want an infinite number of rectangles. And if we want an infinite number of rectangles, then my sigma notation, instead of having n, a number, is going to have infinity in order to produce all of the area shaded under the curve. So we remind you that this indefinite integral notation that we used in section 6.6 at the very beginning is going to represent the true area under the curve of us drawing an infinitely many number of rectangles that are very, very wafer thin, if you will, infinitesimally thin, delta x getting smaller and smaller and smaller. When you think of that idea, that should link you to something that we've done in this course in the fall semester. An idea that tracks the behavior of what happens as my dx, my delta x, gets smaller and smaller and smaller as it approaches 0. That should give you a clue of the next big concept that's going to join with this idea to get us the actual area under the curve. All right, so then the last thing is, whenever we see this definite integral, again, we're accumulating change, we're adding up area, and whenever we see something like this, what we're really doing is we're doing the area from 2 to some number x of this function h of x dx. Hey, did you notice that if I come over here, f of x and delta x become f of x and dx in the definite integral symbol world? So when I look at this, this is the height of the rectangles that we're drawing. This is the width of the rectangles. And this long S looking symbol is really telling us to sum a bunch of areas of rectangles starting at 2 and ending at x. That's what the symbol is trying to tell us. We're going to use rectangles to approximate whenever we can, find the actual retail price. But this is one way that we can practice looking to see what it visually means versus what it symbolically means. The graph of f of x is shown below. Write a definite integral. Again, they don't want us to solve it. They just want to write the definite integral that represents a shaded region. Well, that's pretty straightforward here. We're going to do the integral. Where does the shading begin? At -5. Where does our shading end? At 4. By the way, these are x values. So if they're x values, and maybe I'll do that in this color, if they're x values, then this should be dx. The limits of integration are my starting point and ending point. And then what do I put in here? Well, I need to multiply the heights, which are all based off of f of x, times the widths, which are all dx. So this symbol right here represents the area under the curve. We're going to come back in the last video. We'll take a look at some table problems. We're going to move from graphs to tables to equations. That's kind of the process for this unit. And then we'll get a better understanding, a multi-perspective understanding of definite integrals.